All right, ladies and gentlemen, obviously I'm not here today. I'm gone on school business, but I still want you to take notes and be good for the sub. And today you're going to learn about something called colligative properties. So make sure you have your note packets out and open to where we left off, to the part that says colligative properties. The definition of colligative property itself is a bit of a confusing definition just at first glance. It says a property of solutions that depends only on the number of solute particles, not on the type of solute particles. Now, this is basically saying that a colligative property is something about a solution that will change simply because it has something dissolved. And there are two specific colligative properties that we are going to examine. So colligative property is simply saying it's an aspect of the solution that alters because it has a solute particle. And the identity of the solute particle doesn't matter, meaning this property isn't about what's dissolved in the solution, it's about that there is something dissolved in solution. And it's affected by, it'll be changed by how much solute you have dissolved, not what type of solute you have dissolved. So there are two very specific colligative properties that we're going to look at. The first one is freezing point depression. This is an example of a colligative property. And freezing point depression says if you add any solute, any at all, to a liquid, it will lower the liquid's freezing point. Everybody, trust me, everybody in this class is familiar with this concept. Why? Because we live in Webster, and Webster is in Western New York, and it gets cold and it snows a lot in Western New York. So what do we do to ensure that we're not like the pansies in Virginia who have to shut everything down if there's just the slightest dusting of snow on the road? What do? Well, first of all, we plow, but also we salt the roads. The fact that we add salt to the ice and then the salt melts the ice, that is an example of what I'm talking about here. Freezing point depression. If you add any solute to a liquid, it lowers the liquid's freezing point. This will allow the liquid to stay as a liquid and not a solid at a lower temperature. The freezing point of water is 0 degrees Celsius, 32 degrees Fahrenheit. And we've had a lot of temperatures this winter that have been below freezing, below 32 degrees Fahrenheit. So in order to keep ice from forming on the roads, what do? We add salt to the roads. The salt will dissolve. It gets in with the water and it prevents the water from being a solid. It keeps it at a liquid at a lower temperature. The amount that the freezing point is lowered will increase with more solute added. What this is saying is basically, if we think back to the salting the roads and salting the ice, if you have more salt on the roads, it will drop the freezing point of the water even further. That's what colligative properties are saying. The more solute you have dissolved, the lower the freezing point is going to get. We can turn that freezing point from 32 degrees Fahrenheit. We add a little bit of salt, maybe turn it into 25 degrees Fahrenheit, add more salt, turn it into 15 degrees Fahrenheit, keep on adding salt, and we can keep on melting that ice and dropping that freezing point further and further and further. Now, how do we talk about having more solute in chemistry? We can say that you have more moles of the solute. You can say that you have a higher molarity, right? Because the more moles you have dissolved, the higher the concentration, the higher the molarity, the lower the freezing point. So this freezing point depression is what we call a colligative property. Any solute, any at all, that you add to a liquid will drop the freezing point of that liquid. It will make the liquid stay liquid at a lower temperature. Now, the reason that we use salt, because this will work with any solute at all. Like you could put sugar on the roads and it would melt the ice. You could put Kool-Aid on the roads and it would melt the ice. Hopefully, you're thinking the reason that we use salt, it's economical. it's cheap. We can take salt water from the ocean and evaporate the water and get a lot of salt really quickly. So that's why salt is used. It's available, it's cheap, we can generate a lot of it, but any solute particle, any at all, is capable of doing that. The reason we don't put sugar down, it's going to be more expensive. That's the only reason. It would still work though. So freezing point depression, any solute particle is capable of lowering the freezing point of the liquid that it's in, and the more stuff you have dissolved, the lower the freezing point is going to get. Next up is boiling point elevation. This is the second of the two colligative properties that we're going to be talking about. Again, colligative properties just means something about the solution that changes because it has a solute dissolved in it. The boiling point changes as well. And boiling point elevation says that if you add any solute to a liquid, it will raise the liquid's boiling point. So it does the opposite for the boiling phase change. This, the example that I always talk about in class that deals with boiling point elevation is adding salt to water when you're boiling water to make pasta. There is a huge misconception that the reason that the salt is added to the water is to make the water boil faster. Think about what this is saying. What's up here on the screen. It says if you add any solute to a liquid, it will raise the liquid's boiling point. So adding in that salt to that boiling pasta water is actually doing the opposite of what a lot of people think it's doing. People think it's making the water boil faster. It doesn't. It actually will mean it will take longer for the water to boil, because adding in the salt raises the boiling point of the water, and therefore it will take more energy to get the water to boil, so it will take longer to get the water to boil. The reason that we add salt is not scientific at all. It's simply because it tastes good. It makes the pasta taste good because the pasta itself will absorb flavorings in the water that it's boiling in. So you add some salt to the water, you're basically adding salt to your pasta, and salt tastes good. That's why salt's added, not to make the water boil faster, because it'll actually make the water boil slower, because you added a solute and you raised the boiling point of that liquid. So adding a solute to a liquid increases the boiling point of the liquid, which means that the liquid is going to be a liquid at a higher temperature than normal. So it stays liquid at a higher temp. And just like with freezing point depression, the amount that the boiling point goes up by is directly related to the amount of solute particles added. The more stuff you add to your liquid, the higher the boiling point your solution is going to have. You keep on adding solute, that boiling point is going to keep on going up. The more stuff you have, the higher the boiling point. And how do we talk about amount of stuff in chemistry? We talk about moles, we talk about molarity. So the more moles are dissolved, the more grams are dissolved, the higher concentration of a solution we have, the higher the boiling point. So this point that says on the bottom, so solutes, the presence of a solute will make the solution last as a liquid longer. And what I mean by that, just as a little example, say this is just an example chart, temperature, and we have the freezing point of a liquid, and we have the boiling point of a liquid. We have a normal liquid, a liquid on its own, right? And its freezing point is here, and its boiling point is here. So this is the liquid on its own. If you add in a solute, it'll do two things to the liquid. It will lower the freezing point, and it will raise the boiling point. So what we see is that the solution, so this is liquid plus solute, you have made the liquid capable of staying as a liquid over a greater temperature range. So a solute extends the temperature range over which a liquid is a liquid. It prevents it from freezing, and it prevents it from boiling. It keeps the liquid as a liquid longer. It sort of pushes those boundaries. So water, which normally freezes at 0 degrees Celsius and normally boils at 100 degrees Celsius, if you add a solute particle to it, now you'd be talking about like -5 degrees Celsius for the freezing point, lower, and 105 degrees Celsius for the boiling point, higher. You've extended the temperature range. So we're going to talk a little bit about why. Why does this work? Not simply, oh, okay, well, it does it, but why does it do that? And it has to do with the IMFs of your solvent, of the liquid that you're investigating. I'm going to throw this all up here at once. For freezing point depression, remember that IMFs, intermolecular forces of attraction, it's a comment about how well, in this case, the liquid can stick to the other liquid particles. I'm going to talk about water because water is a very common solvent. So water has very strong intermolecular forces of attraction, like normally, but it needs lots of IMFs when it's a solid, a few less when it's a liquid, and even less when it's a gas. When a liquid freezes, it has to set up basically. It has to start to stick together because it's a liquid turning into a solid. So it has to form lots of IMFs, right? Because you're taking a liquid which can move fairly freely and you're turning into solid. So it's getting stickier. And when you add a solute particle to that liquid, the solute essentially gets in the way of the liquid sticking to itself because the liquid would rather form an IMF with the solute than with the liquid. If you think about salt on the road, because this is what this is talking about, freezing point depression, lowering the freezing point of a liquid so that it is a liquid at a lower temperature. The salt particles, they disrupt the water molecules forming IMFs with themselves. The water molecules start to form IMFs with the salt instead. And in order to form the IMFs with the salt, they have to break the IMFs with each other. Breaking the IMFs with each other is basically turning it from the solid into the liquid. In the solid, the liquid is in the solid form, the compound has IMFs with itself, but you add in a solute particle, the solute gets in the way. It disrupts the solvent from forming the intermolecular forces of attraction with itself. And basically by breaking all of these little IMFs, by the way, in this diagram, these are the IMFs. Basically, all the salt particles are sort of fitting in these spaces, and they're breaking up all of the interactions that water normally has. So they are turning the water from solid into liquid. For boiling point elevation, why does that work? It's based on the same idea. The solute particles in a solution will form IMFs with the liquid. This means, if you sort of think about what this is saying, the water, again, water is a generic solvent here, the water will stick to the solute particle. So if you have, let's think about our boiling pasta water, and you've got salt and water in there. You have salt in your pot. The water that's in the pot is going to form IMFs. It's going to be attracted to the salt. It's going to stick to the salt. Well, think about where the salt is. The salt is in the solution. It's in the liquid form. The salt is not in the gaseous form, which is right above the pot. So if the water is sticking to the salt, the water will not want to evaporate as easily because the salt's not in the air. It wants to stay where the salt is. It has a greater attraction to the salt. And this is what this figure is showing. On the left, you have seawater. So this is our solute plus liquid. And on the right is just the liquid. And we see on the left, the water is sticking to all of the salt ions that are in solution, and it's preventing the water from evaporating. So this has a higher boiling point, right? Higher boiling point because you're keeping the water trapped in solution, so it's going to take more energy to get that water to leave higher boiling point. On the right side, there is no such attraction, so it is easier for the water to boil, so it's going to have a lower boiling point. So basically, you add salt or any solute into water, and the water wants to be a liquid so it can interact and have IMFs and stick to that particular solute. The liquid is the best form for it to interact with, which is why we see the biggest impact on the liquid phase of matter. It lowers the freezing point and it raises the boiling point. Now, not all solutes are created equal, and not all solutes can raise the boiling point or lower the freezing point as well as other things. Basically, ionic compounds are the best at raising the boiling point and lowering the freezing point, and salt is an ionic compound, sodium chloride. The more ions that your compound is capable of breaking into, the more effective it is at lowering the freezing point and raising the boiling point. Covalent compounds are absolutely capable of freezing point depression and boiling point elevation, but they're not as good as ionic compounds. So things like sugar, which is covalent, which is molecular, it's capable of doing it, it's just not as good. And what do I mean by that? Like, why do ionic compounds do this better? Basically because ionic compounds are like awesome 2-for-1 sales. When you add salt to the road, you're adding one formula unit of salt. You're adding like one compound thing of salt. You're adding in NaCl. But NaCl is ionic, and NaCl dissolves in water. So you put in the NaCl, and as soon as it comes into contact with the water, even if the water is a solid, the NaCl will split into its two ions, Na plus and Cl minus. Two parts, two things. Each of those things, the Na plus and the Cl minus, will form an attraction with the water and start to melt the ice. So you put on one thing, but you got two out. It's like a fantastic 2-for-1 sale. You put in one particle, and you got two particles from it. So this is separate from molecular compounds, which do not split into ions. So it's like paying full price for something. You put in one sugar, you get one sugar. It doesn't split into any ions because it doesn't have any ions. It's covalent. There are no ions in covalent compounds. Now, sodium chloride splits into two ions because the formula is NaCl. So I have an Na plus ion and I have a Cl minus ion. And here's what I'm saying. NaCl is twice as effective as sugar because sugar doesn't have any ions. It only has one part. You put one particle in, you get one particle out. Right, you put in C6H12O6, you get C6H12O6. There are no ions, so we're looking for that metal non-metal. All right, remember, ionic, metal, non-metal. This is covalent. This is non-metal, non-metal, non-metal. No ions. One part. But this will also mean that not all ionic compounds are created equal either. Calcium chloride, CaCl2. If you look at this formula, there are 3 ions in this thing because it's CaCl2. I get 1 calcium but 2 chlorides. So I put in 1 CaCl2 and I get from it a calcium plus 2 ion, a chloride ion, and a second chloride ion. There are 3 parts to this particular compound, which means that it is even better than sodium chloride, because this is like a 3-for-1 sale. You put 1 on, you get 3 out. So this is 3 times as effective as sugar, and it's 50% more effective than the NaCl. Sand. Sand is very frequently used and we might be starting to use it this particular winter, when salt stores are running low. If it's been a bad winter, which this winter has been a very bad winter, sometimes cities can't anticipate that. So the amount of salt they have planned to use is starting to run low, and they'll typically turn to sand as an alternative at the end of the winter. Now sand will work. You can put sand on the road, and sand is capable of lowering the freezing point of ice and melting it a little bit, and it provides traction. but it's covalent, so it can't break into any ions. So it's like paying full price. You put one particle in, you get one particle out. So it's like normal. So it works, but it doesn't work as well as the salt. So the question is, what would you rather salt your driveway with in really cold weather? Sand, sodium chloride, or calcium chloride? Well, it is really, really cold, and you want to lower the freezing point of that water quite a lot, because we're well below the freezing point, right? Say it's, we know the freezing point of water is 32 degrees Fahrenheit, and say it's like, on the day that I'm recording this, 5 degrees outside. We want to lower that quite a lot. We want to pick the thing that can split into the most parts. We want to pick the calcium chloride. And if your family has those special de-icer packs for the driveway, or like the special salts, quote unquote special salt, that you lay down on your driveway that they say is, you know, super effective, deep freeze for melting ice at really low temperatures. It's calcium chloride. It's not salt, it's not sodium chloride, it's calcium chloride. And that's why it works as better than the regular salt. That's why they advertise it. Now, just a follow-up question. Which would be most effective at raising the boiling point of water? Most effective? We want to pick something that's ionic and the thing that has the most ions. So in order to sort of answer the question, we just have to go through these options and figure out which one's going to split, which one is going to be ionic and split into the most ions. So ionic, we just figure out which ones are ionic first. So we're looking for a metal and a non-metal. Let's see, magnesium's a metal, fluoride's a metal, so that works. That would be ionic. Potassium iodide, we have a metal and a non-metal, so that one works. Aluminum chloride, aluminum is a metal, chlorine is a non-metal, that one would be good. Calcium phosphide, calcium is a metal, phosphorus is a non-metal, that one would work. C6H12O6, well now we have a case of non-metal. We should automatically eliminate that one because we have ionic choices. We want to get rid of the covalent option. It's not going to be as effective as these salts. And then in determining which of these salts is going to be the best, remember salt is really just a generic term for any ionic compound, we want to look at the number of ion particles that are in it. So in magnesium fluoride, I will get a magnesium, an F, and then a second F. So if this thing has 3 parts, so we're going to bear that in mind. The most ions that it splits into, the better it's going to be at doing this. So potassium iodide, Ki, this will split into K plus and I minus, right? We just look at the subscripts, that's where we're looking, just to be very, very clear. So that thing has 2 parts. So that means that it is not as good as the magnesium fluoride, so I'm going to sort of cross that off right now because I know that the MgF2 is going to be better than it. Aluminum chloride, this is going to split into Al plus 3, and then 1, 2, 3 chlorines based on the subscript. So this thing has 4 parts. Okay, I'm looking at the subscript. So now I'm going to cross off the magnesium fluoride because, again, this is what I'm comparing. I'm seeing that the aluminum chloride has 4 parts. And then the calcium phosphide, when this splits into ions, I'm going to get 3 calcium ions based on the subscript and 2 phosphide ions. So this thing has 5 parts, 5 ions to it, which means that this would be the best out of all of the options for raising the boiling point of water. It splits into the most ions, so it will form the most attraction with the water, and it'll keep the water in the liquid phase longer, and it will really bump up the boiling point, the temperature at which the water boils. So that's colligative properties. The compounds break into, basically compounds that are added to a liquid will lower the freezing point of water, will lower the freezing point of the liquid, and raise the boiling point of the liquid. They'll make it stay as a liquid longer. So you have a test on Wednesday on liquids and solutions. We're going to talk about what is on that test. What do you have to be able to do? Well, we started the unit by talking about vapor pressure, if you'll remember. And let's see, vapor pressure and surface tension. So that's definitely going to be on there, and you'll be asked to read the vapor pressure curve on table H. There will be questions about that. Remember, the vapor pressure curve is saying, what's the vapor pressure of these liquids at different temperatures. And I can also ask about boiling point, because there's a relationship between boiling point and vapor pressure. Essentially, you simply read the curve the exact same way. If I ask what is the boiling point at a certain pressure, just read the pressure and see what temperature it corresponds with. Vocabulary. You need to know what the word solution means, you need to know what the word solvent means, you need to know what the word solute means, and what solubility means. So feel very, very comfortable with this terminology, because it's going to be all over this exam. Again, vocabulary. What does soluble mean? What does insoluble mean? And then table F. Interpreting table F. Table F was the one that has the ions that are soluble, and then the exceptions that make them insoluble, and then vice versa. So remember, insoluble, it doesn't dissolve, it's going to be a solid. And related to that, identify a precipitate. A precipitate, that's a solid that you get from two aqueous solutions. So you're going to say AQ plus AQ yields S. So precipitation reactions. Working with the phrase like dissolves like. This is related to this idea of soluble and insoluble, and it's saying that soluble solvents can dissolve soluble solutes. Polar things dissolve in polar things, and nonpolar things dissolve in nonpolar things. That's that idea right there. Water is polar. Remember that. Water is very, very polar, because polar means different, and we look at the compound and we look at the center molecule, center atom, and everything has to be the same all around the central atom. If there are lone pairs on the central atom, it automatically makes it polar. Ways to get a solute to dissolve faster in solution. So this is like the lab that you did, and factors that affect rate of solution formation. And there were three that we looked at. You might have done a slightly alternate version in the lab, but temperature. If you increase the temperature of the solvent particles will be moving faster, so they can dissolve the solute more quickly. If you stir, agitation, any kind of agitation of the mixture, it brings fresh solvent particles into contact with the solute. It's kind of like you're getting the solvent to move faster. And then the last one was surface area of the solute. That idea that crushing up the sugar actually exposes more of the sugar to the solvent, to the water, and it will get it to dissolve faster. Larger particles will dissolve more slowly because they're actually not as exposed. There's a lot of solute sort of on the middle of the particle that isn't exposed to the solvent, so it'll take a little longer to dissolve. The words saturated, unsaturated, and supersaturated, what those words mean, and going along with that, reading solubility curves. Table G, and remember, table G, it's the solubility curve with all the crazy lines going all over the place. The key to working with that curve correctly is to focus in on the one compound that's being asked about, find that line, and then essentially ignore the rest of it. Solubility of gases. Remember that for most solids, if you increase the temperature, you're going to get the more solid to dissolve. That's for solids, but gases play by different rules. And I want you to, when we're talking about solubility of gases, remember soda. Remember how soda is stored. You keep your soda in your refrigerator, not in your oven. You don't store soda at a high temperature. You store it at a low temperature because it keeps the carbon dioxide dissolved in the soda more effectively. So gases are more soluble at low temperatures and at high pressures. It's like the opposite of when they're ideal, because we want to slow them down. We want to keep them in one place. We don't want the gas escaping. So if we slow them down and we keep the pressure very high, it essentially keeps the gas contained in the liquid. Molarity and parts per million calculations. You will be asked to interpret and perform these calculations on the test. And then lastly, colligative properties, what I was talking about just now. Freezing point depression, boiling point elevation, what compounds are better at it, and why. So the test is on Wednesday. You will need a calculator because there were a few calculations that you did. And for the rest of today, make sure you get your homework turned in on the molarity and parts per million calculations. And I'd like you to use the rest of the period to get started on the review sheet that Sub will has either already handed out or is going to hand out. And I hope you are all very good for her or him. And because if you're not, I'm sure I will hear about it. And I will see you in class tomorrow.